Hi, hello friends. Good evening. Welcome to AS Engineering College YouTube channel. So myself Harikranth Budida, faculty at AS. Okay. So in the last session we discussed about the basics required to analyze any DC circuit, and we already discussed about the basics for solving the DC circuit problems. Okay. And come to the today's session, the most important session today. Okay. So we will discuss about the most important three theorems and which are comes under the basic electrical engineering subject. Okay. Now those are, first one is superposition theorem, second one is Thevenin's theorem, third one is Norton's theorem. Okay. So before I am going to enter into the actual topic, first I will give you the most important details about the theorems. Okay. So in the last session we discussed about the how to calculate the equivalent resistance for the given network, and how to calculate the currents flowing in the individual branches, and how to calculate the power dissipated by the individual elements. Okay. Now for example, if I am going to consider the same problem, but question is apply Thevenin's theorem, okay, or apply Norton's theorem, or apply superposition theorem. If the question is coming like this, then what we need to do? We are not going to applying the traditional method. Traditional method means what? Applying Ohm's law, applying Kirchhoff's current law, applying Kirchhoff's voltage law, and current division rule, voltage division rule. Okay. For example, if I am going to applying the same concept, basic concept for the given network by using superposition theorem, then what happened? There is a difference between these two. Okay. For example, if network consisting of one voltage source and having a multiple resistances, then question is find the total current flowing in the given network. Then how to find the solution for that given problem? First, getting the equivalent resistance from the given network, and use the formula I is equal to V divided by R equivalent, then you will get the value of total current. Okay, that is the normal method. But for example, if suppose the network consisting of multiple voltage sources, multiple current sources, and multiple resistances, then how to find the response? So whenever we are getting, or whenever the network consisting of the more than one voltage source, more than one current source, then if you want to find the solution from the given network, then by using normal method it will take more time. Okay, so that is the reason why in order to reduce the time for the given network, we are going to introducing the theorems. Okay, so that is the reason why the main purpose of theorem is every theorem providing some procedure for getting the results in very less time when I am going to comparing with the actual method. Okay, so that is the reason why theorems are used for getting the solutions for the given network. If the network consisting of more than voltage sources, one voltage source, or more than one current source, or if the network consisting of more voltage and current sources. Okay, so that is the reason why the main purpose of the theorems is getting the solution for any given network if the network consisting of more than one voltage source, more than one current source, or if the network consisting of combination of voltage and current sources. Okay, so first we will discuss about the superposition theorem, then we will enter into the remaining two theorems also. Okay, now first, so I am going to consider the previous most important model from the external examination of university. So this question I taken directly from the university end examination. Now question is, I need to apply the concept of superposition theorem to the given problem, and I need to find the solution. Okay, so now just see here, what is the question? Find the power dissipated by 20 ohm resistor in the following network by using the superposition theorem. Okay, he is asking to find the power dissipated by the 20 ohm resistance, but using what? Superposition theorem. He is not asking the power dissipated by the 20 ohm theorem by using normal method. Okay, he is asking specially, by applying superposition theorem we need to find the solution. Okay, so that is a most important point here. Okay, so find the power dissipated by 20 ohm resistor in the following network by using superposition theorem. Okay, now just observe the given network. So we have one voltage source, that is the value of voltage source is 20 volts, and we have one current source, the value of given current source is 4 ampere, and there are 4 individual resistors are connected in the one combination. Okay, Now question is what now? I need to find, just see, I need to find power dissipated by the 20 ohm resistance. Okay, so how much amount of power is dissipated by the 20 ohm resistance in the following network, and I need to find the solution by using what? Superposition theorem. Okay, so before I am going to enter into the analysis of this problem, first I need to give you the most important key points required to solve this problem by using what? Superposition theorem. Clear? So first, now see, for example, we have one network like this. First we need to identify how many sources are there. Okay, how many sources means it may be voltage source or it may be current source. Okay, but we need to identify how many voltage sources are there, how many current sources are there. Okay, now we observe that in the given network 20 volts voltage source is 1 and 4 ampere current source is 1. It means that for the given network we have only two sources are there. One is voltage source and one is current source. Now what is our target now? Now our target is to find how much amount of power dissipated by the 20 ohms. Okay, so before I am going to enter into the calculation of the power dissipated by the 20 ohm source, actually what is the formula to find the power dissipated by the any resistor? So we are using the formula, that is, what is the formula we are using? P is equal to I square into R. Yes or no? And the unit of the power is always in watts. Okay, now see, question is what? Find the power dissipated by the 20 ohm resistance. So if you want to find the power dissipated by the 20 ohm resistance, the formula we are using to find that value is always what? P is equal to I square into R. Okay, here the value of this R representing what? The value of resistance where you want to find the power dissipation. Okay, so I think this is clear because 20 ohms already given in the problem, so that the value of this R is always representing what? 20 ohms. Okay, now coming to the current. So here I representing the current, but which current I need to consider for finding the power dissipated by the 20 ohm source in the given network? I need to find the value of current which is flowing through the same resistor. Okay, don't consider the value of total current from the given network. If you want to find the power dissipated by one particular resistor, then whenever we are using this formula, you need to substitute the value of current instead of this I, whatever the current is flowing through that particular resistor where you want to find the power dissipation. Okay, so that is the reason why P is equal to I square into R is a formula we are using to find the what? Power dissipated by the 20 ohm source. So that is the reason why what I am going to write here, just I am writing the expression of power dissipated by the 20 ohm, that is, so P suffix 20 ohms is equal to the current flowing through 20 ohms into the value of 20 ohms. Okay, now I need to use this formula for finding the value of what? Power dissipated by that particular 20 ohm source. Clear? So now whenever we are going for the superposition theorem, then what we need to do, first you have to observe one most important point. So in the given network, we identified that there are two individual sources. One is what? One is voltage source, another one is current source. Okay, now while you are analyzing this particular given network, now most important point is when one voltage source is acting alone, then if the network consisting of multiple voltage sources, then the remaining voltage sources all are acting as a short circuit. Okay, once again I am repeating, when one voltage source is acting alone in the given network, then if the circuit or network consisting of remaining voltage sources are other voltage sources, then all other voltage sources acting as a short circuit. Then what about the current sources? Then all current sources are acting as a open circuit. Okay, so this is the most important point. Okay, now we observe that when 20 volts voltage source is acting alone, then whatever the current source is there, that particular current source will act as a open circuit. Okay, so whenever I am applying this particular condition in the given network, then after replacing the open circuit by that particular current source, then the remaining network will becomes as a simple DC circuit. Okay, so remember this point. Whenever I am applying this condition in the given network, then that particular network will becomes the simple DC circuit. Whatever the procedure we followed in the last session, the same procedure we can directly apply to the network after replacing the open circuit by what? Current source. Okay, this is first case. Now coming to the second case. For example, if one current source is acting alone in the given network, then what about the remaining current sources and what about the remaining voltage sources? Simple. When one current source is acting alone, then if the network consisting of any other current sources, then all other current sources will act as an open circuit, and if the network consisting of voltage sources, then all voltage sources will act as a short circuit. Okay, for example, just see here, if this 20-volt voltage source is acting alone, then what happened? That 4 ampere current source is acting as an open circuit. It means what? That particular complete branch I am going to removing, because in open circuit there is no flow of current. So that is the reason why we can directly remove that complete branch. So after removing that particular complete branch, then what happened? Circuit consisting of a network consisting of only one voltage source and remaining only the combination of resistances. Okay. So if that particular network representing what? Only the simple DC circuit. Okay, now I think you are clear. Okay, once again I am repeating. If 20 voltage source is 20 volts voltage source is acting alone, then 4 ampere current source will act as an open circuit. If I am replacing the open circuit by that particular 4 ampere current source, then the remaining network will become simple DC circuit. Okay, now. So in that case, then what is our question actually? Our question is what? Our question is finding the power dissipated by what? That particular 20 ohms current source. Okay, so that particular 20 ohms resistance. Now whenever this voltage source is acting alone, then our target is to find the value of current flowing through this particular 20 ohms resistance. Okay, this is case number 1. Now coming to case number 2, when 4 ampere current source is acting alone, then this voltage source will act as a short circuit. Again our target is to find current flowing through that particular 20 ohm current resistance only. Okay, why? Means as per the definition of superposition theorem, we need to apply the procedure like that. Okay, so that is the reason why first we will discuss about the definition of or statement of the superposition theorem, then again we will enter into the actual network for getting the solutions. Okay, now see here, now this is the statement of superposition theorem. Okay, now read the statement. Any linear and bilateral network consisting of multiple voltage sources, multiple current sources and multiple resistances, then the response in any branch of resistor is the sum of the responses while individual sources acting alone is called as superposition theorem. Okay, once again I am repeating the statement. Any linear and bilateral network consisting of multiple voltage sources, multiple current sources and multiple resistances, then the response in any branch of resistor is the sum of the responses while individual sources acting alone is called as superposition theorem. Now I am going to applying this particular statement for the given network for finding the solutions. Okay, so that is the reason why, just see here. So whatever the points, whatever the theory we discussed, the same theory I am showing here. Just see here. So these are the two important key points whenever we are going for the analysis of any network by using superposition theorem. Okay, just read the note 1. When one voltage source is acting alone, then all the remaining voltage sources are acting as short circuit and the remaining current sources are acting as a open circuit. Okay, just see here, when one voltage source is acting alone, then all the remaining voltage sources are acting as short circuit. Okay, and the current sources are acting as open circuits. Okay, so this is a note number 1 and most important. Okay, now coming to the note number 2. What is note number 2? When one current source is acting alone, then all the remaining current sources are acting as open circuit and all the voltage sources are acting as short circuit. Okay, so based on these two particular points, the complete analysis of the superposition will depends. Okay, now I am going to consider these two particular nodes for getting the solution from the given network. Okay, now see here. So this is a given network. Now what is our target actually? Our target is to find the power dissipated by the 20 ohm resistance. Okay, just now we discussed what is that? What is that? To find the power dissipated by any resistor, we are using the formula. So power dissipated by 20 ohms is equal to current flowing through 20 ohms resistance whole square into the value of 20 ohms. Okay, so just see here. So P suffix 20 means what? Power dissipated by the 20 ohms is equal to, so current flowing through the 20 ohms square into the value of 20 ohms. So this is the formula we are using. Now based on this particular thing, now what we need to do? We need to apply whatever the points we discussed. Okay, now see here. When this particular voltage source is acting alone, then what we need to do? We need to short circuit if the network consisting of other voltage sources. But we observe that we do not have any other voltage sources, so that we are not going to short circuit. Yes or no? But what about the current source? We have one current source. So that is the reason why what we need to do? We need to open that particular current source. So that is the reason why when one voltage source is acting alone, then remaining voltage sources are acting as a short circuit, but we do not have any voltage sources, so we are not disturbing the given network. But coming to the current sources, we have one current source, then that particular current source will act as a open circuit. Got it? Now whenever I am going to applying this particular condition to the given network, then what happen? This particular, okay, so this particular current source will act as a open circuit. Okay, so anyway, just see here, I am going to draw the given network like this. Okay, now just see here, when one voltage source is acting alone, that particular current source is acting as a open path. Now by placing that open path or open circuit instead of current source, I am going to redrawing the given network like this. Just see here, and after redrawing the given network, then the network will becomes as the simple DC circuit which consisting of only one voltage source and the combination of what? Multiple resistances. Just see here. So what we need to do? We need to open circuit this current source like this. Okay, so O dot C means open circuit. Okay, so this is 5 ohms, this is 5 ohms, this one is 10 ohms, and this is again 10 ohms, and this is 20 ohms. Clear? So this particular 20 volts voltage source is acting alone, current source is acting as a open circuit, then the remaining network will becomes like this. Okay, now just observe this particular network. This network representing what? Simple DC circuit consisting of one voltage source and it's a combination of what? Multiple resistances. Okay, now what is our target now? Our target is to find the current flowing through this particular 20 ohm resistance. Why? Because as per the definition, yes or no? Simple. The response in any branch of a resistance is the sum of the responses while individual sources acting alone. Okay. Now, when 20 volts voltage source is acting alone, then what is the amount of current is flowing through this particular 20 ohm resistance? This is the case number 1. Okay. Again, see, when one voltage source is acting alone, then what is the amount of current which is flowing through the 20 ohm resistance? Why means to find the power dissipated by 20 ohms resistance in the given network, first I need to find how much amount of current is flowing through the 20 ohm resistance when individual sources are acting individually. So if I am going to find the value of current flowing through 20 ohm resistance when 20 volts voltage source is acting alone, it means that case number 1 is complete. Case number 1 means what? When voltage source is acting alone, how much amount of current is flowing through 20 ohms is clear. Okay, like that. Again go for the second case. What is second case? When 4 ampere current source is acting alone, then this voltage source will be acting as a short circuit. Then again, how much amount of current is flowing through the 20 ohms? Okay, so when 4 ampere current source is acting alone, then how much amount of current is flowing through the 20 ohms? If we found, then by adding these two currents, it will give the total amount of current which is flowing through the 20 ohms. So after getting the value of total amount of current which is flowing through the 20 ohms, then you can directly use the formula P is equal to, or P suffix 20 ohms is equal to current flowing through 20 ohms square into what? 20 ohms. Okay, so that is the reason why first getting the value of current which is flowing through the 20 ohms is our target. Okay, if you know the value of current flowing through the 20 ohms, then you can directly find the value of power dissipated by the 20 ohms resistance. Okay, so that is the reason why for finding the value of current flowing through the 20 ohms, our target is to apply the condition in the given network for finding this current. That is the reason why what we are doing, when one voltage source is acting alone, current source is open circuited, then how much amount of current is flowing through the 20 ohms? Case number 1. Now case number 2 is when 4 ampere of current source is acting alone, then 20 volts voltage source is short circuited. Again, how much amount of current is flowing through the 20 ohms? So that is the reason why you can observe here, when V is equal to 20 volts voltage source is acting alone, then how much amount of current is flowing through the 20 ohms under case number 1? This is question mark, because our target is to find. Now when 4 ampere current source is acting alone, again what is the value of current which is flowing through the 20 ohms resistance under case number 2? Under case number 2, okay, under case number 2, again our target is to find this. Just see here, when sources are acting individually, then the response we are getting individually. After getting these two individual currents, then what we need to do? Then we need to find total current flowing through the 20 ohms is equal to 20 ohms is equal to, so current flowing through 20 ohms when voltage source is acting alone under case number 1, and current flowing through 20 ohm resistance when current source is acting alone. That is the reason why. So based on this particular equation, you can define the statement of superposition theorem. Just see here, in any linear and bilateral network consisting of multiple voltage sources, multiple current sources and multiple resistances, then the response in any branch is the sum of the responses, when it is possible, when individual sources are acting alone. Okay, again I am repeating, any linear and bilateral network consisting of multiple voltage sources, multiple current sources, multiple resistances, then the response in any branch of resistor is the sum of the responses while individual sources are acting alone. This is the statement of what? Superposition theorem. Clear? So now I am going to applying this particular concept to the given network. Then our target is to find how much amount of power dissipated by the 20 ohm resistance. Okay. Now I am going to start the problem. Okay. Yes. Now this is a given problem. Now see here, what is case number 1? Case number 1 is when 20 volts voltage source is acting alone, then 4 ampere current source is acting as an open circuit. So I can directly write here, when V is equal to 20 volts source is acting alone, then 4 ampere current source, acting as a open circuit. O dot C means open circuit. Simple. 20 volts voltage source is acting alone, 4 ampere current source is acting as a open circuit. Now what we need to do? We need to replace this condition in the given network. So it will becomes what? Simply it will becomes like this. So this is 20 volts voltage source, and here these are the given resistances. Okay, so these are the given resistances. Now what are the values of resistances? 5, 10, 10, 20. So that this one is 5 ohms. So the value of this resistance is 10, and this is also 10, and this one is 20 ohms. Now what we need to do? We need to replace the current source by what? Open circuit like this. Okay, we are replacing the current source by what? Open circuit. So whenever the circuit is open, we can directly say that current value is 0, because current value is always 0 in the open circuit. So that this particular branch, we can directly eliminate this particular branch from the what? Given network like this. Now see, the given network will becomes what? Simple DC circuit. Okay, simple DC circuit. Now what is our target? Our target is to find the value of current. Okay, I am giving the name of the current under case number 1 is I1. It means when 20 volts voltage source is acting alone, then how much amount of current is flowing through the 20 ohms we need to find. Okay, like that, when 4 ampere current source is acting alone, then 20 volts voltage source is acting as a short circuit. Again, how much amount of current is flowing through the 20 ohms. Okay, by adding these two values, you can say that the total amount of current flowing through the 20 ohms representing that particular current. Got it? Now see, so this is a simple DC circuit. Now what is our target? Finding the value of current through the 20 ohms. Now you can see this particular 10 ohms and this 20 ohms both are connected in series. It means that how much amount of current is entered into the 10 ohm resistance, the same amount of current is flowing through the 20 ohm resistance. Okay, so that is the reason why. So as per the concept of current division rule, you can directly find the value of current when the total current is divided into individual branches. It means that if you want to find the value of current flowing through the 20 ohms, you can directly apply that particular current division rule in that particular 20 ohm resistance branch. But to apply that current division rule, first we have to know actually how much amount of total current available at the junction point, because without knowing the value of total current available at the junction point, we cannot apply the current division rule. Okay, so that is the reason why for finding the total current available at the junction point, then what we need to do? First we need to find total. Yes. So to find the total amount of current available at the junction point, first we need to find total equivalent resistance. Okay, so we already discussed about how to calculate the equivalent resistance in the given network. Okay, now we already discussed about that particular procedure also, how to find the equivalent resistance from the given network. Yes or no? So now see, if you know the value of R equivalent, that is equivalent resistance, by using the formula I is equal to V divided by equivalent resistance, then you can find the total amount of current flowing in the circuit. Now this particular total amount of current is starting from the source and it will reach us this particular junction point. Okay. After reaching the junction point, you can directly apply current division rule in the 20 ohms resistance branch. You will get the value of current when 20 volts voltage source is acting alone. Okay. Now our target is to find that thing. Okay. Now you can see. Now step by step we'll find. Yes. Now see. Now we already discussed about the simple DC circuit. Whenever the source is present in the left side, then it is mandatory to calculate the value of equivalent resistance start from right side. Okay. Now while we are observing the right side, 10 ohms and 20 ohm resistance both are connected in series. So now we can directly find. So I am giving the name of the resultant of the two resistances as R1, so that when two resistors are connected in series, then to find the equivalent resistance by directly adding the two values. So that what? 10 plus 20 is equal to how much? 30 ohms. Okay. So 10 plus 20, the resultant as what? 30 ohms. Now you can directly replace this value instead of what? The series combination. Okay. So this is the value of 30 ohms. Now I can directly replace this equivalent resistance for the series combination of these two by what? 30. So that is the reason why I am directly replacing here. Okay. Now see, I am removing the combination of these two and I am replacing the resultant of what? 30 instead of this particular combination. You can directly see, just I am replacing the resultant value of what? Resultant value of the series combination. Okay. Now after replacing the 30 ohms instead of the series combination of 10 and 20, now that 30 ohm resistance is connected exactly in parallel with the 10 ohms. Okay. Now what we need to do? Now we need to find the resultant of this particular combination. So that is the reason why, see here, so 10 and 30. Here 10 ohms and 30 ohms are connected in parallel. Okay, are connected in parallel. Now I am giving the name of the resistance of the equivalent for the parallel combination of 10 and 30 as what? So product of the two resistances divided by addition of the two resistances. Okay, so I am using the scientific calculator for finding the solutions. Okay. Now see, what is the value? 10 into 30 divided by 10 plus 30. Okay. So 10 into 30 divided by 10 plus 30, finally it will give the value of what? It will give the value of 7.5 ohms. Okay. So 7.5 ohms is the equivalent of the parallel combination of those two resistances. I can directly replace this particular combination by what? Now directly I am replacing this particular combination by 7.5 ohms, so that again the network will becomes very simple like this. Okay. Now see here, I am replacing 7.5 ohms instead of the parallel combination of the 10 and 30. Okay. Now after replacing the 7.5 ohms instead of the parallel combination, that 7.5 ohm resultant is connected in series with the 5 ohm resistance. Then the final value of equivalent resistance, I am giving the name of the new resistance for the series combination of 5 and 7.5 as what? R3. So 7.5 plus 7.5 plus 5, it will gives what? 14.5 ohms. Okay. So this is the value of what? Equivalent resistance in the given network. So I can directly replace this combination by what? Directly I can directly replace what? 14.5. Sorry, how much? This is 12 only, na? Sorry, this is 12. Okay, so this is 12. So 7 plus 2, so it will gives 12.5. Okay. Now I can directly replace this R3 by what? Series combination of these two. So the final network will becomes like this. Okay. So final resistance 12.5 ohms. Okay. Now what is the value of voltage we are applying? We are applying the value of voltage as 20 volts. Clear? Now we have the value of voltage and we have the value of what? Resistance. Now by using this voltage and resistance, you can directly find the value of what? Total current. So that is the reason why I can directly use the formula I is equal to applied voltage V divided by R equivalent value, that is equivalent resistance value. Okay. So now we can directly find the value of total current I is equal to applied voltage divided by equivalent value. So that is the reason why we can directly say that. So applied voltage is 20 divided by the value of equivalent resistance as 12.5. So by simplifying this, how much value are getting? Simple, 20 divided by 12.5. So it will give how much? 1.6. Okay. So 1.6 ampere is the value of what? So total current in the given network. Okay. Now our target is what actually? Our target is to find what? Current flowing through what? 20 ohms. So that is the reason why I am going for the actual network. Okay. Now see here. Now I am showing the value of total value of current in the given network after replacing the current source by open circuit. Okay. Now see here. So V is equal to 20 volts. So this is the value of 5 ohms and this one is the value of 10 ohms and this is the value of again 10 ohms and this is the value of 20. Okay. So now after finding the value of total current, after calculating the value of equivalent resistance, so we got the value of total current I is equal to, yes, how much? I is equal to 1.6 amperes. So 1.6 ampere is a current, total current in the network. Okay. Now see here, this particular current is starting from the source and it reaches the junction point now. Now we can directly say that what is the total value available at the junction point now? 1.6 amperes. Okay. Now our target is to find the value of current flowing through the 20 ohms. Okay. So now our target is to find current flowing through the 20 ohms and the name of this current as what? I1, because we are talking about first case. Okay. Now to find that particular current, what we need to do? We need to apply current division rule. Okay. When the current is divided from the total current available at the junction point, it is mandatory to use the current division rule. Okay. Now what is the current division rule formula? So current flowing through 20 ohms is equal to, yes, total current available at the junction point. What is the total current available at the junction point? 1.6. So that 1.6 is the total current available at the junction point into opposite resistance. Opposite resistance means after the junction point, in how many branches that total current is dividing, we need to consider that particular branches. Now we have only two individual branches. Okay. Now while we are calculating the value of current in the 20 ohm resistance, opposite is always 10 ohms only, because out of 1.6 some amount of current is divided and flowing in the 10 ohms and some amount of current is flowing in the series combination of 10 and 20. So that if some amount of current is flowing in the series combination of that particular combination, means the remaining current is directly flowing in the 10 ohms only. That is the reason why 10 ohm is the opposite resistance. So that 10 divided by, now coming to the another point, that is addition. We can also call it as total resistance. Total resistance means what? The sum of the resistances in the individual branches after the junction point in which branches current is dividing. So directly we can say that what? So 10 plus 20. Okay. So see here, as per the current division rule, total current available at the junction point, that is 1.6 into opposite resistance, that is what? 10 because we are calculating the value of current in the 20 ohms divided by sum of all the resistances available in the individual branches. Okay, now by simplifying this, okay, so by simplifying this, how much amount of current you are getting? So 1.6 into 10 divided by 40. Okay, so by simplifying this, you will get 0.4. So that I can directly say that, so current flowing through 20 ohms is equal to 0.4 amperes. Okay, clear? So by using that current division rule, now we found that out of 1.6 amperes, the current flowing in the 20 ohms resistance branch is 0.4. Now we can directly say that out of 1.6, 0.4 ampere of current is flowing in the series combination of 10 and 20 means the remaining 1.2 ampere of current is flowing through the 10 ohms only. Why? Because current is always choose low resistance path. Okay, compared to this 10 ohms, that particular branch consisting of 30 ohms. So whenever the resistance is more in that branch, then less amount of current will flows. So whenever the value of 10 is less compared to the combination of that particular branch, then that is the reason why 1.2 ampere is flowing in the 10 ohms and 0.4 ampere is flowing in that particular combination. Okay, now we found that what? When 20 volt voltage source is acting alone, the current flowing through the 20 ohms is now 0.4 amperes. Okay, now case number 1 is completed. Okay, now coming to the case number 2. What is case number 2? When current source is acting alone, again how much amount of current is flowing through the 20 ohms? Okay, so after calculating this, we can directly add these two currents when individual sources are acting as individually. Then based on that particular current value, we can directly find the value of what? Power dissipated by that 20 ohm resistance by using superposition. Okay, now case number 2. So what is case number 2? So case number 2 is when 4 ampere, okay, so 4 ampere, C dot S means current source, just assume, okay, C dot S means current source. When 4 ampere current source is acting alone, then yes, what is the value of voltage? 20 volt voltage source is acting as a short circuit. Okay, I am not writing the complete sentence here. Okay, when 4 ampere current source is acting alone, then 20 volts voltage source is acting as a short circuit. Okay, now by applying this condition in the given network, then again the given network will becomes what? Simple DC circuit which consisting of only one current source. Now if I am going to draw the given network, now instead of this particular voltage source, what I need to do? I need to short that particular source. So short circuited. Okay, short circuited. Now what are the current resistances are there? So we have 4 resistances. So those are connected like this. Yes. So this is a, and here this particular current source, that is how much? 4 ampere of current source is acting alone. Now this value is how much? 20 ohms. This is 10 ohms. This is 10 ohms and this one is how much? 5 ohms. Now see here, under case number 2, when current source is acting alone, voltage source is short circuited. Again our target is what? Our target is how much amount of current is flowing through? 20 ohms only. Okay, assume the current under the case number 2 as I2. Okay, now our target is to find how much amount of current is flowing through the 20 ohms when current source is acting alone. Okay, after getting this, we need to add the two currents for finding the final solution. Okay, now see, the most important point is when the network consisting of current source, okay, when the network consisting of current source, then no need to find the total current in the circuit, because current to source is there means whatever the current is flowing in the given network, the source of that particular current is always what? Current to source. So that is the reason why remember this point in your mind. when current source is there in the network, don't find the total current. Okay, just apply the current division rule where you want to find the current. Clear? Now you can observe this point. Now 4 ampere of current source is connected here. Now what is the direction of current here? Upwards. It means that what? The 4 ampere of current source, current value is first entered into this particular junction. Okay. After entered into that particular junction, again based on the property of current, what? Current to choose low resistance path. Okay, low resistance path. Now you can see after that particular junction point, so this complete okay, just assume this complete combination will act as a one resistor, and this complete 20 ohm will act as a one resistor. It means what? After the junction point we have two branches. One is what? The combination of this complete resistance branch, and one more is what? 20 ohms. Now out of 4 ampere of current available at the junction point, then how much amount of current is flowing through that particular 20 ohms means you can directly find the current division rule. But how to consider opposite resistance? Can I directly consider 10 ohms? No. Can I directly consider the combination of these two 10 ohms? No. Can I directly consider the 5 ohms as opposite? No. Because out of 4 ampere of current available at the junction point, for example, out of 4 ampere, for example, 1 ampere of current is flowing through the 20 ohms. Then what about the remaining 3 ampere of current is flowing in which branch? That particular 3 ampere of current is flowing in the combination of these 3 elements. That is the reason why opposite resistance, while you are taking the opposite resistance, you need to consider the resultant of these complete branches. Got it? So that is the reason why if I want to calculate the value of opposite resistance, again we are going for what? Getting the equivalent resistance for these 3 particular combinations. Okay. Now for finding that value, just you can observe the given network. Okay. So this 5 ohms is exactly connected in parallel with the 10. Okay. Now whenever the source is present in the right side, you always start reducing or start calculating the equivalent resistance from what? Left side. So current source is there. So that is the reason why what we need to do, we need to consider the value of resistance from the left side. So that while I am considering the value of resistance from the left side, this 5 ohms is connected exactly in parallel with the 10. So now first I need to get the resultant of this. Then after getting the resultant, again that resultant is connected in series with the 10 ohms. So that after getting that particular thing, I can directly apply current division rule in the 20 ohms for finding the solution. Got it? So that is the reason why now what I need to do, I need to find the value of resultant of the 5 ohms and 10 ohms. Okay. So that is the reason why. So 5 ohms and 10 ohms are in parallel. Okay. Are in parallel. Now I am giving the resultant resistance value as a R1. So both are connected in parallel. So both are connected in parallel means how to find the equivalent resistance when 2 resistors are connected in parallel? We'll directly consider product of the 2 values divided by addition of 2. So 5 into 10 divided by, so 5 plus 10. So that is equal to, so R1 is equal to, so 50 divided by 15. Okay, 50 divided by 15. So what is the value of 50 divided by 15? So we can directly say that, so 3.3333. So I'm after calculating you will get, so 3.3333 ohms. Okay, just see here 5 ohms and 10 ohms both are connected in parallel. So after finding the equivalent of the combination of these two, you are getting the resultant as what? 3.3333 ohms. Now I can replace this R1 value instead of the parallel combination of 5 and 10. Okay. So I can replace this instead of that, then the network will becomes what? Reduced. So I am directly replacing here only. Okay. Just see here. So I'm removing this complete combination. Okay. Now I am replacing instead of this by what? Instead of this by 3.3333. So 3.3333 ohms. Okay. After replacing, so So 3.3333 ohms instead of the parallel combination of 5 and 10, then that particular resultant is connected in series with the 10. So that again we need to find the resultant of that. So that particular thing I am giving the name of that combination as R2. So R2 is equal to 3.3333 plus the remaining value is 10. Yes, yes, same combination. So finally you will get the resultant as, so 10 plus 3 means you will get what? So 13.3333 ohms. Okay, now this is the resultant of the combination. It means that now I can replace this value instead of the combination. So finally you will get what? Opposite resistance. Okay, so I am replacing this complete combination by what? Complete combination by this particular resultant like this. Yes, now see here. So I am replacing. So this is actual value. Now we can directly replace the final value as how much? So 13.3333. So that, so 13.3333 ohms is a equivalent resistance of the combination of 3 resistors. Okay, now I can directly say that if I am going to apply current division rule in the 20 ohms, then we can directly say that 13.3333 ohms is the opposite resistance. Okay, the total current available at the junction point is 4 ampere into opposite resistance as what? How much? 13.3333 divided by 13.3333 ohms plus 20 gives the final value of what? Current flowing through the 20 ohms. So that now we can find that value. Okay, so current flowing through 20 ohm resistance is equal to total current available at the junction point. See here, this 4 ampere of current is directly entered into the junction. So that we can say that total amount of current available at the junction is 4 only. So 4 into opposite resistance means what? 13.3333 divided by 13.3333 plus 20. Okay, so now this will give the value of current flowing through the 20 ohm resistance when current source 4 ampere of current source is acting alone. Okay, now we can simplify and find the value. So 4 into 13.3333 divided by, so 33.3333. So by solving this you will get the value of 1.5999. Okay, so 1.5999 amperes. Okay, so this is what current flowing through the 20 ohm resistance when the current source is acting individually. Okay, so finally, as per the statement of superposition theorem, any linear and bilateral circuit consisting of, yes, multiple voltage sources, multiple current sources and multiple resistances, then the response in any branch, it means what? The response, the current in the 20 ohm resistance is the sum of the responses, okay, while individual sources acting alone. Okay, now we can directly say that, so by superposition theorem, okay, so SPT means just assume superposition theorem. So current flowing through 20 ohms is equal to the value of current under case number 1. What is the value of case number 1 current? Yes, what is the value? 0.4. 0.4 ampere of current is flowing through the 20 ohm resistance when 20 volts voltage source is acting individually. Now 0.4. Now when current source is acting alone, the value of current flowing through the 20 ohms is how much? 1.599. So I can directly add these two values. So 0.4 plus 1.599. Okay, so 0.4 plus 1.99. So by adding 999, I think 999, by adding these two, so you will get what? So you will get the value of final current as, yes, 1.5 means, so 1.5 9999. Final value is so 1.9999 amperes. Okay. So this is the value of total current flowing through the 20 ohm resistance by applying what? Superposition theorem. Now we can say that for finding the value of power dissipated by the 20 ohm resistance by using the superposition theorem concept, first we need to find the current flowing through 20 ohm resistance only. Now finally we got the value of current flowing through the 20 ohm resistance. Now after knowing this value, you can directly go for what? P is equal to square of current which is flowing through the 20 ohms multiplied with the value of 20 ohms. It will give the value of what? Power dissipated by the 20 ohm resistance in the given network. Okay. Now we can directly go for the final value. So that is, so current flowing through 20 ohms is equal to, so 1.9999 amperes. Okay. 9999 amperes. Now finding the value of power dissipated by, so power dissipated by 20 ohm is equal to, okay, 20 ohm resistance is equal to current flowing through 20 ohm resistance square into the value of 20 ohms. Okay. So now the value of current, substitute the value of current, so 1.9999 whole square into 20. So now simplifying this, just simplify. So 1.9999 square into 20, it will gives the value as 79.992. Okay. So it will gives 79.992 watts. Okay. So this is the amount of power dissipated by the 20 ohm resistance by using what? Superposition theorem. Okay. So this process is applicable for any network or any DC network if the network consisting of multiple voltage sources, multiple current sources and multiple resistances. Okay. Once again I am finally defining the statement. Any linear and bilateral network consisting of multiple voltage sources, multiple current sources, multiple resistances, then the response in any branch of resistor is the sum of the responses while individual sources acting alone. So as per this definition, we can say that when voltage source is acting alone, you got the value of current through what? 20 ohms. That is case number 1. Now when current source is acting alone, again you found the value of current flowing through the 20 ohms. By adding these two, you got the final value of current by using superposition theorem. After getting the value of current, then you can directly find the value of power dissipated by the any resistor in any network like this. Okay. So this particular concept is applicable for all the networks. Okay. If the network consisting of that thing. Okay. So same procedure you can use in the end examinations also for finding the solutions by using superposition theorem. Okay. So this is about the superposition theorem. Now we'll discuss about what? Now we'll discuss about the Thevenin's theorem. Okay. So this is also directly taken from the end examination and most important and most of the time repeated in the end examination. Okay. Now what is the question? Read once. By using Thevenin's theorem, find the current in 6 ohm resistor and also find the power dissipated by 6 ohm resistor shown in the network. Okay. So again same question is what? Find the power dissipated by the 6 ohm resistor in the given network by using what? Thevenin's theorem. Here also same. Okay. Thevenin's theorem is also used to find the solution when the network consisting of what? Multiple voltage sources, multiple current sources and multiple resistances. But when comparing the superposition theorem, the procedure is completely different in case of Thevenin's theorem. So what is the difference between these two we'll discuss and we'll solve this problem by using the Thevenin's theorem. Okay. Now here the most important point is whenever we are going for the Thevenin's theorem, so Thevenin's theorem will providing one 2-terminal open equivalent network. Okay. So 2-terminal equivalent network this theorem is providing. Now based on that particular equivalent circuit, we need to solve this problem. Okay. So to find the solution by using Thevenin's theorem, we have one procedure. What is that procedure? We'll discuss. Then we'll enter into the actual concept. Okay. Now First we are going to enter into this particular Thevenin's theorem problem. First I will give you the procedure. What is that procedure? Simple. First procedure is identify the load resistance. Okay, identify the load resistance in the given network and disconnect from the original network. Okay, first one is what? Identifying the load resistor in the given network and disconnect from the original network. Then after disconnecting the load resistance, then the remaining circuit will becomes or representing the two terminal linear network. Okay, we require that particular point here if you want to solve the problem by using Thevenin's theorem. Okay, identify the load resistance in the given network and disconnect from the original network. Then after disconnecting the load resistance, whatever the remaining network is there, that particular remaining network is representing two terminal linear network. Okay, this is step number 1. What is step number 2? Step number 2 is by using the Thevenin's theorem, we need to convert that particular two terminal linear network into the two terminal equivalent circuit of a Thevenin's theorem. Okay, so after replacing this particular two terminal linear network by the equivalent circuit of the Thevenin's theorem, then you can find the solution very easily. So that is the reason why what we need to do, first we need to identify the load resistor, disconnect from the network. Then we need to convert the remaining two terminal linear network into the two terminal equivalent circuit provided by the Thevenin's theorem. But how to find this particular how to convert into two terminal equivalent circuit of Thevenin's theorem? By finding the values of two important parameters. One is what? One is calculation of Thevenin's voltage, and another one is calculation of Thevenin resistance. But where we need to find these two? We need to find these two values across the open terminals where we disconnected the load resistance. Okay, so where we disconnected the load resistance across that particular two terminals only, we need to find the Norton's resistance and we need to find the we need to find the Thevenin resistance, and also we need to find the Thevenin's voltage. Okay, so while we are calculating these two particular points, we need to follow again most important key points. That is, while you are calculating the value of Thevenin resistance across the open terminals where we disconnected the load resistance, that time if a network consisting of voltage sources, then all voltage sources are short circuited, and if the network consisting of current sources, then all current sources are acting as a open circuit. After replacing short circuit by voltage sources, open circuit by current sources, then the network consisting of only the resistors. So that by using series and parallel combination of that particular resistances, you can easily find the Thevenin resistance across what? The open terminals. That is what? Point number 1 for getting the value of what? Thevenin resistance. But how to find the Thevenin voltage? Thevenin voltage is finding again across the open terminals where we disconnected the load resistance. But here finding the value of Thevenin voltage means finding the voltage drop across the resistor which is exactly connected across the open terminals. Okay, so after getting these two, we can directly substitute these two values in the equivalent circuit of Thevenin's theorem, and whatever the load we disconnected initially, that load is connected across the open terminals of a equivalent circuit of Thevenin's theorem. And again same procedure, I is equal to V divided by R equivalent. By using that you can find the current flowing through the load resistance. After finding the current flowing through load resistance, you can use a formula. P is equal to square of current into the value of resistance is what? Power dissipated by that particular resistance. Okay, so that is the reason why first we will discuss about the definition statement, and after that we can directly apply this procedure to the given network for finding the solution. Got it? Now, so we already completed this part. Okay, so by using Thevenin's theorem, find the current in 6 ohm resistance and also find the power dissipated by 6 ohm resistance shown in the network. Okay, so just see here, he is asking to find current flowing through the 6 ohm resistance and also power dissipated by the 6 ohm resistance. So from this we can say that in the given network 6 ohm resistance is the load resistance. Got it? So we need to disconnect that load resistance from the given network. Now we need to redraw the network after replacing after disconnecting the load resistor. Okay, so that is the first step. Now coming to the first important point, that is statement. After that we'll apply direct to the network. Okay, now see here statement. Any two terminal linear network any two-terminal linear network consisting of multiple voltage sources, multiple current sources and multiple resistances can be replaced. Okay, this point is most important. Can be replaced by a two-terminal equivalent circuit consisting of voltage source connected in series with the resistance is called as Thevenin's theorem. Okay, so as per this particular statement, I can directly say that this is a given network. We identified that this 6 ohm resistance is the load resistance. Okay, now step number 1 is what? We need to disconnect. Okay, so we need to disconnect the load resistance. Okay, I am not writing anything here, just note down. Okay, now step number 1 is what? Disconnect the load resistance from the original network and redraw the remaining network here. Okay, so I am disconnecting that, so I am redrawing the remaining network like this. Okay, so this is the 5 ohm resistance and this one is what? 4 ohms, and after disconnecting the load resistance, the remaining network will, okay, so this is how much? So this is 4 ohms. So this one is 5 ohms and this is 3 ohms and the value of applied voltage is how much? 5 volts. Okay, see here, this is the original network. We identified that 6 ohm resistance is the load resistor, so that we identified the load resistor and we disconnected that, so that the remaining network will becomes like this. Now this network is representing two-terminal linear network. Okay, two-terminal linear network, because terminal A and terminal B already we given the names for the two terminals. Okay, two-terminal linear network. Now what we need to do in the step number 2, we need to convert this complete two-terminal, or we need to replace this complete two-terminal linear network by what? Equivalent circuit of Thevenin's theorem. Okay, so what is equivalent circuit actually? Equivalent circuit of Thevenin's theorem is two terminal. For example, this is also terminal A and here, so for example, this is terminal B. Okay, now we already discussed in the statement, what is that? Replaced by, can be replaced by two terminal equivalent circuit consisting of one voltage source connected in series with the resistance. So that what? This voltage source is representing Thevenin's voltage. Okay, so this is V suffix TH means Thevenin's voltage, and this resistance is representing Thevenin resistance. Okay, so we need to replace this two-terminal linear network by this particular two-terminal equivalent circuit consisting of one voltage source connected in series with the resistance. But how it is possible? How it is possible? Simple. It is possible by finding the value of Thevenin's voltage and Thevenin resistance from what? This particular two-terminal linear network. But how it is possible to find this, and where we need to find these two? We need to find these two values across the terminals where we disconnected the load resistance. So where we disconnected the load resistance? Here. So that is the reason why we need to find the value of Thevenin's voltage and Thevenin's resistance across the open terminals where we disconnected the load resistance. Got it? So that is the reason why what we need to do, if we want to replace the complete two-terminal linear network by this two-terminal equivalent circuit, it is possible by calculating the Thevenin's voltage and Thevenin resistance across the open terminals where we disconnected the load resistance. Okay, so now our target is to find that particular Thevenin resistance and Thevenin voltage across these two terminals. Okay, now while we are calculating the Thevenin voltage and Thevenin resistance, what are the key points we need to apply? Okay, now first one is, for example, I need to find the value of Thevenin resistance across the terminals. Okay, now how it is possible? Simple. Now see, for example, anyway I will draw the same circuit here. Okay, now I am drawing the same circuit here. Okay, now see, so if you follow this particular procedure, while you got the question in the end examination based on the Thevenins, you can directly apply this. Okay, you can directly apply this procedure. Okay, now I think same, yes or no? So 3 resistors and 1 voltage source. Okay, now just see here, this is 5 volts and these are the 2 terminals, these are the 2 terminals and the value of 3, 5, 4. So that this one is 3 ohms, so this is 5 ohms and this is 4 ohms. Yes, I think right. So no, 3, 5, 4. Okay, 3, 5, 4. Yes. Now first, whenever I want to find the value of Thevenin resistance across the open terminals like this, then what I need to do, what are the changes I need to do in this particular network? Simple. While you are calculating the Thevenin resistance across the open terminals where we disconnected the load, you have to short circuit all the voltage sources. For example, if network consisting of 5 voltage sources, then for example 2 current sources, then if you want to find that particular Thevenin resistance across the open terminals, you need to short circuit the voltage source and open circuit the current source. It means what? If 5 voltage sources are there, means you need to short circuit all the 5 voltage sources. And for example 2 current sources are there, means you need to open circuit the 2 current sources. After replacing that, then the network will consisting of what? Only resistances. That particular network representing what? Only the network consisting of resistances. We already discussed in the first session. That is what? Getting the value of equivalent resistance. Use the series and parallel combination for finding the equivalent resistance or Thevenin resistance across the open terminals. Now for that, what I need to do now? For finding that, I need to short circuit this, because network consisting of only 1 voltage source. If more than 1 voltage source, you need to short circuit all. Okay. If network consisting of current source, you need to open circuit all. But we do not have any more than this particular voltage source, so that I need to short circuit this. That's it. Okay. Now see here, I'm simply short circuiting this. Short circuit means what? Yes, short circuit means what? Simply I am showing short circuit like this. Okay. So now see here. So this is short circuited. Now observe the given network. We do not have any voltage sources. We do not have any current sources. So that we can say that terminals are in the right side. So that for getting the value of Thevenin resistance, you need to start reducing from what? Left side. While we are reducing this particular thing, then you need to observe that 3 ohms and 5 ohms both are connected in parallel. First to find the equivalent of that. After getting the equivalent, then you need to observe that resultant is connected in series with the 4 ohms. So after finding the equivalent of the series combination of this resultant and 4, you will get the what? Equivalent resistance in this particular network. That equivalent resistance is exactly appearing across the terminal A and B. So that equivalent resistance is representing the Thevenin's resistance. Okay. Now first find the values. So I am using calci for finding this, in order to reduce the time required for this. Okay. Now first 3 and 5 ohms. Now 3 and 5 ohms both are connected in what? Yes. Now otherwise you can directly find here. Now see here. So first thing is what? So 3 ohms and 5 ohms. 3 ohms and 5 ohms both are connected in parallel. So I am giving the name of the equivalent resistance for the parallel combination of 3 and 5 as a what? R1. Now when 2 are connected in parallel, then how to find the equivalent resistance? By considering what? So product of that 2 resistances divided by what? So addition of that particular 2 resistances. We already discussed about this, how we are getting this formula. Okay, we already derived the same formula in the last session. Okay, now 5 into 3 divided by 8. So what is by simplifying this, you will get what? So by simplifying this, you will get the value of, yes, find the value, how much? So 15 divided by how much? 8. 15 divided by 8 means you will get what? 1.87. 1.875. So this is what? So this is the value of equivalent resistance of what? Parallel combination of these two. Okay, parallel combination of these two. Now replace this value instead of this parallel combination. Okay, now it will becomes what? Now it will becomes like this. Okay, so now we can directly say that what? I am replacing here only, because I need to Yes. Now see here, I am replacing here. Yes. Now replace this value here. Yes. So 1.875. So this value, this is also 0. You need to erase this one also, na? 5. Now I am replacing this value here. So after replacing, you can observe that 1.875 ohm is connected in series with the 4 ohms. So 1.875 ohms. Okay, after replacing this value, instead of that particular parallel combination, then 1.875 ohm is connected in series with the 4. So that by adding these two values, you will get what? R equivalent, that is equivalent resistance. Because what? We do not have any more resistances. We have only two resistances. Both are connected in series. Just add these two values. So 4 plus 1.875. It will give how much? So 5.875. Okay, I am writing directly here, but you have to do with your own. Okay, so equivalent resistance is equal to 5.875. Now what I need to do? I need to replace this value instead of the series combination, so that it will becomes what? It will becomes like this. Okay, so this is terminal B and this one is terminal A, and we are calculating the value of Thevenin resistance what? Across the open terminals where we disconnected. So this value is the equivalent value, so that the value is how much? 5.875. Okay, so 5.875 ohms. Now see here, this is the equivalent value and this equivalent is directly appearing across the terminal A and B. So that what? So RTH, that is Thevenin resistance, is equal to equivalent resistance. So finally we got, that is, so Thevenin resistance across the open terminals where we disconnected the load in the given network is calculated, and that value is representing 5.875 ohms. Okay, 5.875 ohms. Now we calculated the value of Thevenin resistance across the open terminals. Now what is pending now? Getting the value of Thevenin's voltage. Okay, so getting the value of Thevenin's voltage, and this value is also calculated across the open terminals where we disconnected the load. So now for that, what I need to do? Again I am drawing the same network here, and now I am going for what? Calculation of the V Thevenin, that is Thevenin's voltage. Now see here. So just follow the procedure for any problem. If problem based on the Thevenin's theorem, you will get the solution very easily. Okay, so now, yes, now this is what? Terminal A, and this is terminal B. Now our target is to find the Thevenin's voltage across the open terminals. So what is the value of voltage here? What is the value of applied voltage? 5 volts. Okay, so just see here, after disconnecting that 6 ohms, now we are finding the Thevenin voltage across that open terminals. The same circuit I replaced here. Just see here, this is the circuit. Okay, so the value of applied voltage is 5, and this is the value of 3 ohms, and this one is how much? I think this is 5, I think. Yes or no? Yes, 5 and 4. Okay, now this one is 4 ohms and this is 5. So this one is what? Sorry. So this is 5 ohms. Now you can replace. So this is 5 ohms. Yes. So we have taken the original network after disconnecting the load. Now our target is to find what? Thevenin's voltage across the open terminals where we disconnected the load. Now here the most important point is, while you are calculating the Thevenin's voltage across the open terminals, it is very simple. Okay, how it is possible means, we know that in the parallel circuit or in the parallel combination, voltage is same but current is not same. But in series circuit or series connection, current is same but voltage is not same. It means if I am going to connecting one voltmeter across the terminal A and B, it means that this 5 ohm branch and this complete combination both are in parallel. It means that parallel voltage is same. So that is the reason why what I am doing for finding the value of VTH across the open terminals, if you want that value, you can directly find that value by knowing or by calculating the voltage drop across the 5 ohms. Okay, you can observe here. If you know the voltage drop across 5 ohm resistance here, this voltage drop is directly appearing across the terminal A and B. It representing what? Thevenin's voltage. Okay, because if I am going to connecting one voltmeter across the terminal A and B, whatever the voltage is there, the same voltage is available in the this particular parallel branch also. So that is the reason why if you know the value of voltage drop across 5 ohms, it means that the same voltage is appearing across the terminal A and B. That is the reason why finding the Thevenin's voltage across the open terminals means finding the voltage drop across the resistor which is exactly connected across the terminal A and B. Okay, I think you are clear. Okay, finding the Thevenin voltage across the terminal A and B means finding the voltage drop across the 5 ohm resistor which is exactly connected across the terminals A and B. So that is the reason why simply we can say that, so this complete path is open. So when this path is open means you cannot consider the 4 ohms with what? The combination of this. So by applying that point, you can say that 3 ohms and 5 ohms both are connected in series. These two are connected in series means you can directly say that 3 plus 5, 8. 8 ohm resistance you know and 5 volts already there. So I is equal to 5 divided by 8 ohms gives the value of current. So that current is starting from here and it will reach as what? This point. After reaching that point, that current is try to move or try to divide in 2 branches. But we observe that what? 5 ohm branch is closed path. But that particular 4 ohm is what? Open path. So that is the reason why, because of the open path, whatever the current is there at the junction point, the total amount of current is flowing through 5 ohms like this. Got it? So whenever this current is flowing through 5 ohms, that current multiplied with the value of resistance gives voltage drop. What is the formula we are using to find the voltage drop across resistor? V suffix R, that is voltage drop across resistor, is equal to current flowing through that resistor multiplied with the value of that particular resistor gives the voltage drop across that particular resistor. Got it? So that is the reason why what we need to do, while we are calculating the value of Thevenin's voltage across the terminal A and B, no need to go for another procedure, just apply this concept, you will get the value of Thevenin's voltage. Okay, now for finding the value of VTH, now our target is to find voltage drop across this. Now for finding the value of voltage drop across this, now whatever the discussion we discussed, apply that. Okay, now you will get the value of what? That thing. Now see here, now first our target is to find total current in the network. Now see here, so the applied voltage is 5 volts. Now we identified that is, we need to find the value of VTH across open terminals A and B only. But this 4 ohms comes under the open branch, so that while calculating the value of current, no need to consider that value. So the same network, if I am going to draw here, it will becomes what? Like this. Just see here. So if you know the analysis of simple DC circuits, you can easily find the solution if the problem comes under what? Individual theorems. So this is 5 volts, this is how much? This is 3 ohms and the value of this is how much? 5 ohms. Now see here, that branch is open, so that open branch current cannot flow, so that I am removing that complete branch because I need to find the voltage drop across this 5 ohms only. Okay, if you want to find the voltage drop across these 5 ohms, first we need to find the equivalent resistance, then go for the current. After current flowing through the 5 ohms, that current multiplied with the 5 gives a drop. So that is the reason why both are connected in series, so that I can directly say that both are connected in series means equivalent resistance is equal to how much? 3 plus 5. Okay, so 3 plus 5. So 3 plus 5 is equal to how much? 8 ohms. Now we calculated the value of equivalent resistance. Now if after knowing this particular value, then finding the value of current. Okay, so anyway, for understanding, better understanding, what I am doing, simply I am replacing this resultant instead of this. Okay, now see here, that value I am replacing here. Now what is this value? 8 ohms. We have resistance value, we have voltage value. Now you can directly say that what? So current I is equal to, yes, V divided by R, that is equal to, what is the value of voltage, applied voltage? 5 divided by, what is the value of resistance? 8. Now what is the value of 5 divided by 8? 5 divided by 8 means what? How much? So 5 divided by 8 will give 0.625. So I is equal to 0.625 amperes. Okay. So while you are going for the external examination, you must carry the scientific calculator for reducing the time required for what? Solving the problem. Okay, that is the reason why I am using here. Okay, so finally we can say that what? The value of current to total current flowing in the particular circuit is what? Now 0.625. Now this particular current is starts from what? This point, and first it will reach as what? This junction point, and that current is observing that is there any path to flow. So that current identified that this is open path. So current cannot flow. The total amount of current is flowing through 5 ohms now. Okay. Now we can say that what? Now this is most important step actually. So if you know the procedure, then only you can find the solutions. Okay. So this is how much? 5 ohms. Now this is how much? 3 ohms. Now this is how much? 4 ohms. Now see, current flowing through this 5 ohms. How much now? 0.625 only na? 0.625 amperes. Okay. Now if you know the value of resistance, if you know the value of current flowing through that resistance, you can directly find the voltage drop across that particular resistor. Got it? Now what is our required, what actually we required? We required voltage drop across 5 ohms. Okay. So V is equal to I into R formula. As per this formula, so voltage drop across 5 is equal to current flowing through 5 ohms into the value of 5 ohms. Okay. So now we already calculated the value of current 0.625. Okay. So 0.625 into the value of 5. So simplify this value, how much? So 0.625 into 5. Okay. So it will give what? 3.125. Okay. So 3.125. So this is what? This is voltage drop across what? 5 ohm resistance, which is exactly connected across the open terminals. Now we require this value for finding what? V Thevenin. So I can directly say that the value of Thevenin's voltage across the open terminals where we disconnected the load, is given by the voltage drop across the 5 ohms. Okay. Now the voltage drop across this value is representing what now? 3.125. So that I can directly say that 3.125 volts is the voltage drop across this 5 ohms. Okay. Now this value is directly appearing across the terminal A and B. So that we can say that the Thevenin voltage, across the open terminals where we disconnected is given by, so V Thevenin is equal to 3.125 volts. Okay. Now we calculated the value of Thevenin's voltage, we calculated the value of what? Thevenin resistance also. Now we can say that what? That complete 2-terminal linear network can be replaced by what? 2-terminal equivalent circuit consisting of Thevenin's voltage connected in series with Thevenin resistance. Now can I directly replace the 2-terminal network by equivalent circuit of Thevenin's theorem by substituting these two values? Yes. So that is the reason why we can directly say that, so Thevenin resistance and Thevenin voltage. So this is Thevenin resistance and this is Thevenin. This is Thevenin voltage. Okay, now we have two terminals like this. Okay, so this value is what? V Thevenin. Okay, now what is the value of V Thevenin? 3.125. Substitute here. 3.125 volts. Now what is the value of Thevenin resistance? We already calculated. 5.875. Substitute that value also. 5.875 ohms. Okay, it means that what now? This equivalent circuit is replacing instead of what? Instead of what? Instead of what? This thing. Got it, I think? Yes or no? This two-terminal linear network can be replaced by two-terminal equivalent circuit consisting of Thevenin voltage and Thevenin resistance. But to replace that particular equivalent circuit, we require the calculation of Thevenin resistance and Thevenin voltage. We calculated these two values across the open terminals where we disconnected the load, so that I can directly replace this complete two-terminal linear network by this. I think you are clear. Okay. Now finally, we converted or we replaced two-terminal equivalent circuit. Okay, by what? Two-terminal linear network. Now final step is what? Our target is actually what? Current flowing through 6 ohm resistance and power dissipated by the 6 ohm resistance. Okay, so current flowing through 6 ohm resistance and power dissipated by 6 ohm resistor means, actually where is the 6 ohm here? We do not have that 6 ohm in the equivalent circuit. That is the reason why the last step is connect the load resistance in the across the open terminals of the equivalent circuit of Thevenin's theorem. Okay, are you getting my point? Connect the disconnected load resistance initially from the given network and replace that load resistance across the open terminals of the equivalent circuit of Thevenin's theorem, and then find the value of current flowing through it. That gives the final response. Okay, so that is the reason why now what I need to do, I need to connect the load resistance which is initially disconnected from the original network across what? These two terminals. Now we can directly say that what? So this is what now? 6 ohms. Okay, 6 ohms. Now our target is what? How much amount of power is dissipated by 6 ohms and what is the value of current flowing through 6 ohms? If you want to find the power dissipated by 6 ohm resistance, first you have to find how much amount of current is flowing through that particular thing. That is the reason why first what we need to do, we need to find how much amount of current is flowing through that particular 6 ohms. Now you can observe we have one voltage source and there is a combination of resistances in series. So find the equivalent resistance, and I is equal to VTH divided by addition of these two gives what? Current flowing through 6 ohms, because in the series connection current is same. So whatever the current is flowing through the RTH, the same current is flowing through 6 ohms. That is the reason why you can directly find this value by using what? Like this. Okay. So I is equal to VTH divided by equivalent resistance. Equivalent resistance means both are connected in series. I can directly substitute like this. So RTH plus what? 6 ohms. So here I is equal to, what is the value of VTH? 3.125 divided by what is the value of RTH? 5.875. So 5.875 plus 6. So this value I is equal to, just use a calculation and find it. Okay. So how much? 3.125 divided by how much? 11 point. Okay. So 11.875. It will give the value of what? 0.2631 amperes. Okay. So this is the value of what? Current flowing through the 6 ohm resistance by using Thevenin's theorem. Okay. Now what is the last point here? The last point is how much amount of power is dissipated by the 6 ohms. Okay. So for that, what is the formula we are using? Simple. So power dissipated by the 6 ohms is equal to current flowing through 6 ohms whole square into the value of that particular 6 ohms here. Okay. Now that is equal to, what is the value of current flowing through 6 ohm resistance? 0.23. Okay, 0.2631. So 0.2631 whole square into 6, that is equal to, yes, use a calculation and find the value. So what is the value of this? Yes, so 0.2631, okay, 2631 into how much? 6. It will gives the value as 0.4153. Okay, so this is the power dissipated by 6 ohms. Okay, so always in the watts. Okay, so this is the power dissipated by the 6 ohm resistance in the given network by using what? Thevenin's theorem. Okay, I think you are clear. Okay, simple. Again I am repeating. First, identify the load resistance in the given network and disconnect from the given network. Then the remaining network will becomes what? 2-terminal linear network. Now step number 2 is what? I need to replace that 2-terminal linear network by 2-terminal equivalent circuit of the Thevenin's theorem by calculating the value of what? Thevenin resistance as well as Thevenin's voltage. So how to find the Thevenin voltage and how to find the Thevenin resistance we discussed. After getting these two values, we need to replace the two values in the equivalent circuit of the Thevenin's theorem and connect the load resistance across the open terminals of a Thevenin's equivalent circuit, and by using the I is equal to VTH divided by RTH plus load resistance, you can find the value of current through the load resistor. After that, you can directly find the power dissipated by that load resistor by using Thevenin's theorem. Okay, so this is the procedure to find the power dissipated by any load or any resistor by using Thevenin's theorem. Okay, now I think you are clear. Okay, now the last topic is, that is what? Norton's theorem. Again here we considered one most of the time repeated the same problem in the university examination, so that I have taken this. So see here, by using Norton's theorem, determine the current through 5 ohm resistor and also find the power dissipated by 5 ohm resistor in the following network. Okay, so here the most important point is the 50% of the procedure we followed in the Thevenin's theorem is same as that of the Norton's theorem also. Okay, up to the calculation of Thevenin's resistance, the same procedure in case of Thevenin Norton resistance. It means what? Whatever the procedure we used in the Thevenin's up to the calculation of Thevenin resistance, the same procedure we are following in case of the Norton's theorem also. What is that procedure? Identifying the load resistance in the given network is step number 1. Now we need to convert the remaining 2-terminal linear network into the equivalent circuit provided by the Norton's theorem, and which consisting of what? One current source connected in parallel with the resistance. Okay, the most difference between these two is what? The equivalent circuit of Thevenin's theorem is different and the equivalent circuit of Norton's theorem is different. Okay, but up to the calculation of Norton resistance and Thevenin resistance, procedure is same. Okay, so now this is the given question. So by using Norton's theorem, determine the current through the 5 ohm resistor and also find the power dissipated by the 5 ohm resistor in the following network. Where is the 5 ohm resistor in the given network? This one is the 5 ohm resistor. Just see here. So this is 2 ohms, this is 12 ohms, this one is 3 ohms and this is 5 ohms. Okay, and the value of applied voltage is how much? 10. Okay, now that thing is a 5 ohm resistor. It means that in the question they ask to find the current flowing through 5 ohms as well as current flowing through what? The power dissipated by what? 5 ohm resistance. So that is the reason why 5 ohm is the load resistor. We need to disconnect that load from the given network. That is step number 1. And the remaining procedure is what? So replacing the 2-terminal linear network by the equivalent circuit of the Norton's theorem, which consisting of one current source connected in parallel with the resistance. But how it is possible to find the value of Norton's current and Norton resistance? Same procedure. Norton resistance is also calculated across the open terminals where we disconnected the load resistance. Okay, but while we are calculating the Norton resistance, then voltage sources, all voltage sources are short circuited, all current sources are open circuited. Then the circuit or network consisting of only resistances. Use the series and parallel combination for finding the value of what? Norton resistance across the terminal A and B. Got it? So anyway, after completion of this problem, you will get full clarity how we are applying the procedure for finding the solutions from what? Norton's theorem. Got it? Now before I am going to enter into the analysis, first I will give you the statement now. Okay, what is statement? See here. Any two-terminal linear network consisting of multiple voltage sources, multiple current sources and multiple resistances can be replaced, okay, can be replaced by a two-terminal equivalent circuit consisting of current source connected in series with, in parallel with the resistance. Okay, concentrate on this particular point, okay, from this point to this point. Okay, so current source connected in parallel with the resistance. Okay, it means what? So we can directly say that current source is this one, current source is this one, connected in parallel with the resistance, in parallel with the resistance, and it is a what? Two-terminal equivalent circuit. So current source connected in parallel with the resistance is called as what? Norton's theorem. So this resistor is representing Norton's resistance. So Norton resistance is always represented with R suffix N, and this current source is representing with what? Norton's current, I suffix N. Okay, so now we need to convert or replace given network. Okay, just see here. After replacing this, after disconnecting this 5 ohm resistance from the given network, then the network will become what? Two-terminal linear network. That linear network can be replaced by this equivalent circuit. But how it is possible? It is possible by calculating the value of Norton's current and calculating the value of Norton resistance. Okay, so getting the value of Norton resistance is same as that of the Thevenin resistance which we calculated in the Thevenin's theorem. But coming to the calculation of Norton's current, the procedure is completely different. Okay, so now what we need to do? We need to find the response, that is power dissipated by the 5 ohm resistance from the given network. Okay, so that is the reason why you can observe that any two-terminal linear network consisting of multiple voltage sources, multiple current sources, multiple resistances can be replaced by a two-terminal equivalent circuit consisting of current source connected in parallel with the resistance is called as Norton's theorem. Okay, so this particular two-terminal equivalent circuit representing the equivalent circuit of the Norton's theorem. Okay, now we need to get that particular response by using what? Norton's theorem. Okay, now we already discussed about the procedure. What is the procedure? First thing is identifying the load resistance in the given network and disconnect from the network. Okay, now if we disconnected that, step number 1 for example. Okay, so step number 1, what is step number 1? Identifying the load resistor and disconnect from the original network. Then the remaining network will becomes what? Two-terminal linear network. I am drawing that two-terminal linear network here. Okay, now see here. So this is what? This is the two-terminal linear network after disconnecting what? After disconnecting the load resistance from the original network. Okay, now this is what? 2, 12, 3. So this one is 2 ohms, this is what? 12 ohms, and this is how much? 3 ohms. Now what is the voltage we are applying here? 10 volts. Clear? This is original network. We identified load resistance, we disconnected from the original network, then this network will becomes like this, and this network is representing two-terminal linear network. Clear? Now what I need to do? I need to replace this complete two-terminal linear network by what? Equivalent circuit of Norton's theorem. But how it is possible? It is possible by using, by calculating Norton's resistance and Norton's current across or what? At what? Across the terminals A and B. Okay, so that is the reason why I am writing here. So we need to calculate the value of Norton resistance, that is R suffix N, and also we need to calculate the value of current. Okay, now here the most important point is, if you want to find the value of Norton current across the open terminals where we disconnected the load resistance, this voltage is short circuited. Then 2 ohms and 2 ohms connected in parallel. Find the equivalent resistance. Then the equivalent resistance is connected in series with the 3 ohms. Then finally you will get what? R equivalent, that is equivalent resistance. Now that equivalent resistance is appearing across the terminal A and B. So that equivalent resistance representing Norton's resistance. Clear? Now coming to the Norton's current, how to find the Norton's current? Simple. To find the Norton's current, what we need to do? We need to short circuit the terminal A and B where we disconnected the load resistance. Okay, it means what? Just see here. This is most important step. Okay, many of the students are doing mistakes while they are calculating the value of what? Norton's current. Now see, if you want to find the Norton's current, what we need to do? We need to short circuit these two terminals like this. Whenever these two terminals are short circuited, then what happens? Definitely some amount of current is flowing through this particular short circuited path, because we have what? Voltage source is there. So that whatever the current is flowing through that particular short circuited path, that current representing what? Norton's current. Okay. Now to find that particular Norton's current, what we need to do? First we need to find the total current available at the junction point, because to find that particular current in the that particular short circuited branch, what we need to do? First we need to find the value of total current available at the junction point, because that is possible by applying current division rule only. If you want to apply current division rule in any branch for finding the current which is divided from the total current available at the junction point, what we need to do? First we have to find the current available at the junction point. But to find that particular current available at the junction point, what we need to do? First finding the equivalent resistance in the given that particular network is required. If you know the equivalent resistance, then I is equal to 10 volts divided by that equivalent representing total current, and that current is starting from this point and it will reach as the junction point here. After knowing the value of total current available at the junction point, you can directly apply current division rule in this branch for getting the value of what? Norton's current. Got it? So that is the reason why what we need to do now first we need to find Norton's resistance, then go for the calculation of Norton's current. After finding these two values, what? Substitute in the equivalent circuit. Then whatever the load resistance we disconnected initially, that resistance, load resistance connected across the open terminals or terminals of a Norton's equivalent circuit, then find the value of current through that particular load resistance and find the power dissipated by that load resistance also. Okay, this is the procedure to apply what? Norton's theorem to any given network. Okay, now first thing is, first we need to find what? First we need to find, yes, resistance, Norton resistance. So where we need to find the Norton resistance? We need to find the Norton resistance across the open terminals where we disconnected. Okay, now anyway I am going for the step number 2. Okay, now step number 2. Step number 2 is what? Finding the or calculation of Rn. So that I am writing here. So calculation of R suffix n question mark. Our target is to find this. Okay. Now I am going for the what? 2 terminal linear network. So this is what? So apply the procedure, that's it. Okay, you will get the value of what? Anything. Okay. Now what is the value of resistance? 2, 12, 3, and this is 10. So this one is 10 volts, this is 2 ohms, this is 12 ohms, and this one is how much? I think 3. Yes, 3. So this is 3. Now we need to follow the procedure if you want to calculate the Norton resistance. Whenever we are calculating the Norton resistance, we already discussed voltage source must be short circuited. Okay, current source must be open circuited. But we have only one voltage source in the given network. So that what? We need to short circuit this and find the R equivalent. Okay, now you can see this. So we are replacing short circuit instead of voltage source like this. Just see here. So this is short circuited like this. Okay. So I am writing S dot C, it means short circuited. Okay. Now after replacing the short circuit instead of the voltage source, now you can see 2 ohms and 12 ohms both are connected in parallel. Now find the equivalent of that particular combination. Now find the value of equivalent calculation. Yes, what is the value? Yes, calculate everyone. Yes. So now we can directly say that what? So both are connected in parallel, otherwise I am writing here. Okay, anyway. So I am giving the name of the equivalent resistance of the parallel combination of 2 and 12, that is 2 into 12, product of the two resistances divided by addition of the two resistances is equal to, so what is the value of this? It will give a value of, okay, 24 divided by 14, it will give a value of 1.7142, okay. So 1.7142 ohms, okay. So everyone must carry the scientific calculator while you are going for what? End examinations, okay. So now I need to replace this parallel combination by this equivalent, okay. I am replacing here only because it will take more time to draw the network again and again, okay. So just follow the procedure and copy everything, you will get the clarity, okay. Now anyway, now this is a value of what? 1.7142 ohms, okay. Now after replacing this resultant, now this value is connected in series with the 3 ohms, okay. Now we need to erase this one also because already we replaced that thing, okay. Now these two values are, these two resistances are connected in series. So now I am going for the calculation of the series combination of these two, and I am giving the name of that particular two new resistance as R2. Now 1.7142 plus, what is the value of remaining 3? So the value of R2 is equal to 1.7, sorry, we have the value of final value, that is how much? 3 plus 1 means 4.7142 ohms, okay. So now if I am going to replace this value instead of this thing, then it representing what? Final equivalent resistance, okay. See here, I am replacing this 4.7142 instead of the series combination, okay. So now you can see here, so this is the value of 4.7142 ohms, okay. Now see here, this R2 value I replaced instead of the series combination, so that 4.7142 ohms is the equivalent value of resistance in that particular network. Now we can directly say that what? If this is equivalent resistance, this equivalent resistance is directly appearing across the terminal A and B. So we can say that what? This equivalent resistance is also called as Norton's resistance. So that is the reason why what we need to do? We need to say that R equivalent is equal to Norton's resistance is equal to, what is the value? 4.7142, okay. So 4.7142 ohms, okay. So this is the equivalent resistance, clear? Now finally we got the value of Norton's resistance, okay. Now what is the remaining thing is what? Getting the value of Norton's current, okay. So now how to find the Norton's current? Norton's current is calculated by short circuiting the terminals A and B where we disconnected the load resistance, okay. This point is most important, most of the students are doing mistake at this calculation only, okay. So after disconnecting the load resistance in the original network, so this is what? This is the actual network, okay. Now I think this is how much value of voltage? 10 to 12, 13, 3, yes or no? So this is 10 volts, this is 2 I think. So this is 2, yes. So this is 2 ohms, this is 12 ohms, and this one is how much? Yes, how much I think? 3, yes, sorry. So this is 3, okay. Now this is the two terminal linear network after disconnecting the load in the original network. Now our target is what? finding the value of what? Norton's current only. Finding the value of Norton's current means just a simple short circuit these two like this. Okay, short circuit these two terminals like this, then definitely some amount of current will flows through this particular short circuited branch. That particular current representing the Norton's current. But to find that current, it is mandatory to apply the actual applied voltage in the given network. So that what? Now you can observe, if you want to find the current flowing through that particular short circuited path, first we have to find what? The total current available at the junction. Because to find that current, we need to apply current division rule. If you want to apply current division rule, it is mandatory to know the value of total current available at the junction point. So that is the reason why first finding the value of total current available at the junction point is first point. But to find that current, how much amount of voltage source is supplying that current? So for that what? If you know the equivalent resistance, then we can directly find that current, because I is equal to, that is current I is equal to applied voltage divided by equivalent resistance gives the value of total current in the given network. Okay. Now the point is, if you want to find that Norton's current, first find the value of total current available at the junction. To find that particular current, first to find the equivalent resistance. After finding the equivalent resistance, use the current formula for finding the value of current. Clear? So that is the reason why first we need to, what we need to do? We need to find equivalent resistance first. But for finding the value of equivalent resistance, what we need to do? We need to observe one most important point. Whether in the network, voltage source is present in the left side or right side. If source is present in the left side, then start calculating the equivalent resistance from what? Right side only. Okay. Now you can see 3 and 12 ohms both are connected in parallel. Then you will get the equivalent resistance of the parallel combination of those two. Now after getting the equivalent resistance, that equivalent resistance is connected in series with the 2 ohms. So that finally you will get the equivalent resistance. After getting that, find the value. Okay. Now first find the value of this thing. Okay. Now you can see. So 3 ohms and 12 ohms both are connected in parallel. Okay, I am writing like this, just I am using like this. Okay. So both are connected in parallel. So that I am giving the name of the current, I am giving the name of the new resistance, that is equivalent resistance of the parallel combination of these two as what? 3 into 12 divided by 3 plus 12. Okay. So what is the value of this resultant? Okay. How much? 3 into 12 divided by, so 3 into 12 divided by, yes, what is the value? So 3 into 12 divided by 3 plus 12 means you will get what? 2.4. Okay. So I am using scientific calculator for finding exact values of this. Okay. Now R1 is clear. Now what I need to do? I need to replace this value instead of the combination of this. Okay. So now I am replacing here only because it will take more time to draw the, okay, draw the network now. Now you can see. Now you can see. So now I am replacing this value as how much? 2.4. So this is 2.4 ohms. Now see. After replacing the 2.4 is exactly connected in series with the 2 ohms. So I can directly say that, yes, otherwise I will calculate this value here also. Okay. Now see here, what is that? 2 and 2.4. 2 ohms and 2.4 ohms both are connected in series. So that I am using the name for the new value of resistance as R2. So R2 is equal to 2 plus 2.4 is equal to 4.4 ohms. Okay, 4.4 ohms. Now I can directly replace this value instead of what? The combination of these two like this. Okay. Now finally you got the value of what? Equivalent resistance. So you got the value of equivalent resistance, that is what? 4.4 ohms is equal to R equivalent. Okay, R equivalent. Now you can find the value of current. Okay, so now you can find the value of current, that is how much? I is equal to 10 divided by 4.4. Now I is equal to V divided by R equivalent. R equivalent. What is the value of V? 10. What is the value of resistance? 4.4. Okay. So solve the value. Solve and tell me. So 10 divided by 4.4 means how much? So 10 divided by 4.4 means 2.2727. Okay. So this value is what? 2.2727 amperes. Okay. So this is a value of what? Current in the given network like this. Okay. Now we can directly say that what? This is a total current supplied by the source when we are calculating the Norton's current. Now I will draw the actual network here with the voltage source like this. Okay. So now okay, so this is the short circuited path. This is terminal B and this one is terminal A, and here this is Norton resistance. This is 3 ohms. This one is how much? 12 ohms. This is how much? 2 ohms. What is the value of applied voltage? 10. Now this current value is coming from this point and it will reaches this particular junction. Now what is the value of total current available at the junction? 2.2727. Okay. So now 2.2727 ampere is the value of total current available at the junction. But our target is what? Finding the value of Norton's current. So now to find that particular calculation of Norton's current, it is possible by what? Current division rule. Apply current division rule in the short circuited branch of the Norton's current or in the terminal A and B path, you will get the value of Norton's current. Okay. Now we can directly say that what? So IN, that is Norton's current, is equal to total current available at the junction. That is how much? 2.27 into opposite resistance is how much? Yes. After the junction point, in how many branches the current is dividing? In 12 ohm branch and in 3 ohm branch. So 2.2727, out of the 2.2727, some amount of current is flowing through 3 ohm branch, means the remaining current is flowing through 12 ohms only. Okay, that is the reason why opposite is always what? 12. So that is the reason why 12 divided by addition of the two values. Okay, that is what? 3 plus 12. I think you are clear. Yes or no? This complete value. 2.2727 is the total current available at the junction into opposite resistance 12 ohms divided by 12 plus 3. So by solving this, you will get the value of what? So by simplifying this, 2.2727 into 12 divided by, so 15, it will give the value of, so 81816 amperes. Okay, 1.81816 amperes. Now this current is representing what? Norton's current. Okay, now I can replace these two values in the equivalent circuit of what? So equivalent circuit of Norton's theorem. So what is Norton's theorem equivalent circuit? Current source. Okay, current source connected in parallel with the resistance. So this value representing Norton's and this value representing what? Norton's current. That is Norton resistance, and this one is what? Norton's current. Okay. Now I can directly replace, or now I can place these values here. Norton's current is equal to 1.81816. So this value is what? 1.81816 amperes. Okay, this is. Now what is the value of Norton resistance? Norton resistance is how much? Norton resistance is 4.7142. Okay, so now this value is 4.7142. Okay, now this is two terminal linear network only na. Sorry, this is two terminal equivalent circuit only. This is terminal A and this is terminal B. Okay, now you can see we replace the two terminal linear network by two terminal equivalent circuit of Norton's theorem by calculating Norton's current by short circuiting the terminals where we disconnected the load, and Norton's current calculated across the open terminals where we disconnected the load. Okay, finally that two terminal linear network can be replaced by this two terminal equivalent circuit. Now what is final task actually? Power dissipated by the 5 ohm resistance, that is load resistance. And also if you want to find the power dissipated by the load resistance, you can first you need to find current flowing through that particular resistance. Okay, now I think 5 ohm resistance is the load resistance, yes or no? Once see that value. Yes, 5 ohms only na? Yes, 5 ohms only. Now come to this step. So after calculating these two values, what we need to do? We need to replace or connect the load resistance across the terminal A and B of a equivalent circuit of the Norton's theorem like this. Okay, now this value is how much? 5 ohms. Now what is our target actually? Our target is to find the current flowing through 5 ohms and find the power dissipation by the 5 ohms also. Okay, now observe again this final network. Okay, we have current source and we have one resistance and we have the load resistance 5 ohms. So Norton resistance, load resistance both are connected in parallel and we have current source directly. So to find the current flowing through the 5 ohm resistance, you don't find the value of total current again and again because we have current source in the network. So this particular 1.81816 is the current which is directly reaches the junction point. Okay, now because the direction of current is upward, so that this current is reaches the junction point. After reaching, it means what now? 1.81816 ampere is the total current available at the junction point. Based on what? The direction of this current. Clear? Now our target is to find what? Current flowing in 5 ohms. Now you can directly apply current division rule in the 5 ohm resistance, that is what? In the load resistance for finding the what? Current flowing through the 5 ohms. Okay. Now whenever we are finding that particular current in the 5 ohms, so total current available at the junction is 1.81816. Opposite resistance is Norton's resistance divided by addition of these two resistances gives what? Current flowing through the 5 ohms. Now go for that. Okay. So current flowing through load resistance, that is what? 5 ohms is equal to total current available at the junction, that is what? 1.8181, I think how much? 6. So total current available at the junction is this much and opposite resistance is what? Rn. Okay. So I am directly substituting that value. Rn is how much? 4.7142. So 4.7142 is the opposite resistance. Now divided by sum of resistance or total resistance. Total means what? 4.7142 plus 5. Okay. So now 4.7142 plus 5. Okay. So now our target is to find this value. Okay. Now use scientific calculator and find it. Okay. Now what is the value of this? So 1.81816 into 4.7142 divided by, so 4.7142 plus 5. So by simplifying this, you will get the value of current as 0.8823334. Okay. So this is the current flowing through what? This is the current flowing through the load resistance by using what? Norton's theorem. So finally we got the current flowing through load resistor. Now what is the remaining now? Remaining is power dissipated by the load resistance. Okay. Now go for that. Okay. So power dissipated by 5 ohms is equal to current flowing through load resistance, that is 5 ohm resistance square into the value of 5 ohms. Okay. Now what is the value of current flowing through 5 ohm resistance? 0.8823334. Okay. Substitute that value. 0.8823334 whole square into the value of 5. Okay. Now this value representing what? Power dissipated by the 5 ohm resistance by using Norton's theorem. Yes. Now calculate 0.8823334 whole square into 5. It will give what? So it will give the value of 3.892566 and the unit of power is in watts. So this is the analysis of what? Norton's theorem. Clear? So now I think you are clear with the concepts of what? Superposition theorem, Norton's theorem and Thevenin's theorem. Clear? So remember one thing, theorems are always applied when the network consisting of multiple voltage sources, multiple current sources and multiple resistances. Okay. So by using the traditional method for finding the solution from any given network, it is possible. Okay, definitely it is possible, but it will take more time. Okay, that is the reason why by applying the theorems, you can get the solutions very quickly, and the time required for the theorems is very less compared to the time required for the traditional methods. So that is the reason why superposition theorem, Norton's theorem, Thevenin's theorems are the most and most important. Okay, so most and most important. So I think you are clear with the how we are going to applying the theorems on the given problems. So anyway, please do subscribe ACE Engineering College YouTube channel for more useful content. Thank you so much.